Okay. So everything should be fine. Good. Good morning. So maybe you don't know me. I just introduced myself a little. My name is Benam. I'm postdoc here and working with Niels regarding to sediment engineering and river engineering. You see so many pictures on your slides from Tiber River or Albania. So I am working with all of them. Okay. And today we are going to work with sediment transport and bed load, suspended load. But before that, we are going through a Kahoot test. It's just a game. So do you have any experience with Kahoot? Anybody? So you are familiar with that, yes? So just with your phone going to Kahoot, the website, and then log in. It's just a game for your, so we have a problem with this. Mona, can you hear me? Kamal?
Yes.
Yes, and you see the Kahoot webpage, yes?
Yes.
Yes, good. So you are ready for. So just put this pin. It's just a game and a race. And if you don't know about it, the time is important for your scores and just a game for preparing you for the course. Put your name. Who is Kay? Who is Kay? Nobody?
Yeah, it's me.
Oh. K, me, ABC. Come on, I restart it. Put your name. What is K? What is ABC? Now it's work. Thank you, Kamal. Everybody? Everybody in? Let's start. So the first question is just for your warm up. Okay. So true or false? And be careful about the time. It's true, push through. So we are working on Kahoot. I think someone coming to the room. Yes. So go to Kahoot website and log in. This is the pin code at the bottom of the page. So ready for the next one? Okay, it's easy. Choose the meandering river. Yeah, giving somehow can be a meander. This is not a braided river. Oh. So you know the braided river? You see so many parts of the rivers, deviation from the main stream. So it's called braided river. It can be maybe 10% meandering, but in previous question, the best answer should be the A. So if you have question, just stop me. Yeah, interesting. 12 false. Be careful about the knot. The value of kinematic viscosity for water.
There's -7
10 to -5, -3, -6, -7.
Yeah.
So do you have any question? Yeah, you see the correct answer.
Okay.
So double points. Does not increase erosion.
Maybe it's slow vegetation and resistant flow and sediment sense.
Good. 14, I think it's good. Where can I show you? So vegetation can keep the soil material. So it's not bad for erosion because it's not allowed to collapse the soil material and keep with its roots. So it's good for avoiding erosion generally.
Okay.
Yeah, Sujit Cunning. Which one is silt and clay sediment? The material is silt.
It's gravel.
It's not so big picture, but no. Green is the bigger one, the coarser material. So clay should be a fine sediment. It's not so hard question.
Crazy.
Not cohesive sediment.
No, it's crazy. It's just like stick.
Oh, so fine material sediments is cohesive. If you have any question, just ask me. True or false, double point. So we have some shapes of sediments here. It's belong to upstream or downstream. Imagine we have a river reach.
It's a downstream.
It may be for upstream or maybe for downstream of a river basin or river reach. Look at the corners of sediment particles or the shape of it.
Oh.
Good. Yeah, because you can see we have the sediment particle has some corner. You can see, so they don't face to erosion. So they should be for upstream of a river reach, because during the river, they collide to each other and make some erosion, and the shape will be completely circle or a sphere. No question?
Mm-hmm.
So this one is an important question. So hydraulic ratios for a wide rectangular river.
Maybe 2i.
It's so easy.
It's area over perimeter. No.
We need it during the course today.
Why?
Yeah,
Shit.
so easy, but so R is A to P.
Yeah.
Yeah, and Y regarding to B is so small, so it should be Y. Yeah, it's not working here. Okay, I will tell this. The meaning of aggradation.
Ninja. Aggregation.
Good. So aggradation is the opposite one. This is the meaning of what? Degradation. Yeah. Aggradation or deposition of sediment, it's input more than output sediment.
Arasahojit.
Yeah. So another easy question. Which software or code can simulate or consider sediment? But be careful, HECRAS in new versions just can consider the sediment. And I think you work with SIM and HECRAS in your previous courses. And RIF3D and of course SIM, both of them developed at NTNU. Double point. Which one can be wash load? A or B or both or none of them? Two seconds. Good, 15. Yeah, wash load is a suspended load and it's not on the bed. So A should be correct. Interesting question. Albert Einstein has some formula in sediment engineering in our course. It's funny question, yes? So what is the correct answer? Yeah. Yeah, exactly. Albert Einstein is a father. So he is famous for physics or quantum, but his son is famous in our field. It's a funny question. Armor layer, you have it in previous lecture. Good. Yes, armor layer. There is like a armor who defends from the fine sediments and avoid erosion. I will show you more pictures. Yes. There is armor layer in this picture. Yes, for example, here you can see there are so many coarse material or coarse gravel, and also here. So these are avoid of erosion of fine material behind of them. Where is Kamal? You are going? True, false, double point. Bruce number or Russ number. You can anticipate both bed load and wash load with Russ number. Yes, if you remember the graph, you can estimate both. Sujit move. Good question. Manning equation. Oh, 10. Yeah. Also, you have it in your previous lecture, and it's an important question. Manning roughness or Manning, not roughness, Manning equation is valid for turbulent flow. It's not so accurate in laminar flow. So what is the Manning coefficient of a glass? Easy question. Yes. Others are so high. So maybe for a river with gravel, the Manning roughness should be around 0.03 or 2. Double points. So it's false. So you cannot see all forces in this picture. Which force is missing? Yeah, the weight of a particle, gravity. So we have another force downward here, which is so important. Last question. You are so near to each other. So it's a Sheets parameter. And tau star C is critical value. Yeah, 13 is good. So when your shear stress is more than critical, so you have movement. If not, you don't have. Yeah. It's not so bad. Yeah, but everyone is near to each other. Good. Who is Yi Yang? Yeah, and Saroj? Yeah, and Sujit. You have to be better. Good, so we review some topics, and then we can go through the lecture. So before starting, let me just yeah, we have a problem here. So I need to restart this, but it is better to do it later. Yeah, it's not working. Okay, let's go through this and then I will explain it later for you. I want to tell you a story of sediment transport, both wet load and suspended load, but the tablet is not working and I have to restart it. So I go through the slides and then come back and give you some information. So here you can see bed sampling. This is a sample and you can see how to trap the sediment particles there. And sometimes it's good to sampling, sometimes not, and you can see the movement of sediments. So here it's good catching the sediment. So we have debris or obstacles in front of the sampler. And here you see armor bed, so we don't have any sediments going to the sampler. You can see a score, and while you see the scoring, look at the movement of sediments. And here is the bed sample that you can see these are uniform sediments. So we are going through bed load transport modes, dimensional analysis, and review of important parameters and approach for determination of bed load transport rate. So let's start with the way of moving sediment. The term bed load defines all particles which are transported along the riverbed in a rolling, a sliding, and saltating. You can see here rolling, sliding, it's just go straight, saltating, and or jumping. I will explain them after the rest because I need the tablet. So according to this definition or assumption, each researcher choose one assumption. One of them choose that the sediment moves based on rolling. One of them choose that sediment moves based on a sliding or saltating. And then they provide some equations and some research. But the main point, like previous equation or previous parameters that you want to consider it, you need a dimensional analysis. You may remember the dimensional analysis methods such as P. Buckingham. You may remember that. Then we want to evaluate the sediment transport. We define it as GS, and you can see the dimension or unit of that, kilogram per second. And if you want to consider it in, for example, 1 meter, so it should be kilogram per meter multiplied by second. So it depends to some parameters that you can see here. For example, the parameters of fluid properties, it's the fluid density and kinematic viscosity. For the sediment properties, it's density of sediment, rho S means sediment, D is grain diameter or sediment particle diameter, channel, so we use the water depth of channel and the shear velocity of the channel. And kinematic parameter, G, which is 9.8, the gravitational acceleration. In various references, you can see we have 8 parameters, in some 7. So you know from the dimensional methods that we can convert these parameters to each other. So here we consider 8 parameters. And you know from P-Buckingham that we have 3 main dimensions, such as length, mass, and time. So meter, kilogram, and time, second. And we have 8 parameters. So our dimensional analysis or dimensionless parameters should be 8 minus 10, 5 parameters. Okay, if you have any question, ask me. So this is our first dimensionless parameter, and the other one is particle Reynolds number. You can see the definition here. Dimensionless transport rate is introduced as this parameter. The sediment transport rate to sediment density, diameter, and shear velocity. The other one is particle Reynolds number. You can see the definition, and you should use the grain diameter instead of D. The other one is Shields number, which you have it in previous section. And yes, there is some problem here, but it's tau 0 over 2 rho S minus rho multiplied by GD. And the other one is density term. So rho prime, it's important that rho prime is dimensionless. So it's rho S minus rho divided to rho. And the other one is relative submergence, the water depth over 2D. We work with these parameters. This is the reason that I mentioned them here. So after doing or finishing the dimensionless analysis, we have some final questions. So I just want to remind you some definition for Reynolds number, and you should know that Reynolds number is different with particle Reynolds. We have two kinds of flows. First is laminar flow, and the other one is turbulent. For the laminar flow, the Reynolds should be below 2000, and for the turbulent, the Reynolds should be more than 2000. But just consider the transition. The transition should be between 500 and 2000. Here in this slide, they consider it as laminar flow. And I want to remind you the logarithmic velocity profile, which we use for turbulent flow. It's not the usual one or the yeah, it's not working. So consider that we have in turbulent flow, we have a logarithmic velocity. And for the laminar flow, you have this equation here. So here UZ, it's the velocity of the specific point in height. And U star is the shear velocity, and nu and Z. So if you want to compute a velocity at a height of Z, you should find the velocity of that specific height and then put Z here, and H is the water depth. And if I want to remind you the laminar flow versus, you can see it's a laminar flow and the streamlines are straight, then we increase the velocity or increase the discharge, you can see the turbulence in the streamlines, and it's not a straight line. So this is turbulent flow, and it occurs mostly in high velocity and high discharge. No question? Oh. So I also want to remind you the Reynolds star, which is the particle Reynolds number. Be careful about this definition and don't confuse it with Reynolds. So this is the shear velocity multiplied by D and divided to nu, the kinematic viscosity. And you remember that if the Reynolds star or Reynolds or particle Reynolds number is more than 70, the regime is rough. And we have a sublayer in each water profile. The sublayer dimension or the sublayer height is computing with this equation. Delta is equal to this equation, and you can see when you want to use these equations, for example, this one or this one, here you have you want to compute it for this elevation. So you should put Z equal to this value, and then you have the mean value of velocity. So be careful, you use the mean velocity. So particle Reynolds number can be combined with sheet stress, resulting in a new parameter. So some researchers develop or introduce a new parameter mostly for rough regimes that you can see here. It's D star and it's named sedimentological grain diameter. And the definition is this equation. The definition is Reynolds star power 2 to the sheets parameter. And the power is 1/3. And if you insert this value, you have this parameter. And after introducing D star, they try to introduce some figures, and then by those figures, you can consider which regime do you have and which flow kind do you have. It's another representation of sheets diagram. And for a predefined material with given DC and density, the star depends only on the kinematic viscosity. So kinematic viscosity also depends on temperature. So somehow it depends on the temperature. But the influence of viscosity in general negligible for Reynolds star more than 70. If you remember the graph, in the turbulence regime, it's not important. Further parameters that you should know and remember, it's the shear stress is gamma RS, or if you insert of gamma, you have rho GS. And this is for wide channel. Maybe it's your question, Mona. It's in the Kahoot test. R for wide, rectangular rivel is Y. So shear velocity is this equation, tau 0 to rho, and critical shear stress, this important equation. That is mostly we computed as this value, 0.047. So rho prime, it's a dimensionless density. If you remember in some slides before, adequately considered via shear stress, relative submergence, which is water depth over 2 diameter, has an effect on the bed load transport rate. However, for large relative submergence means more than 100. The bed load transport rate is not significantly affected by the relative submergence. So if you have this condition, the epsilon or relative submergence is not so important. So other important parameters that we faced in this course, it's the absolute bed shear stress. So this is tau 0 means gamma RS, and this is tau star, which is the equation that I show you. Tau 0 over to the rho S minus rho multiplied by GD. So you remember this question in the Kahoot test. If we have this condition, what's happened? Kamal, are you here?
Yeah.
So if we have this condition, what's happened? We have movement or not? Everyone think about it. So our shear stress is less than critical one. So we don't have any movement because the critical one is more. So the difference of these, tau 0 minus tau C, you can see it here. It's called excess shear stress. And I think it's an easy definition and you understand it. Relative shear stress is a way to make the shear stress dimensionless, and we divide tau 0 to tau C or the other parameters. And relative excess shear stress is like that. And you can see the equations here. So in your example after our class or in other problems, if you see they ask you what is the excess shear stress, you have to compute this parameter. Or if they ask you what is the relative excess shear stress, you have to compute this parameter. Okay, maybe you need 10 minutes rest, yes? Yes. So we meet each other at 9:15 or yeah, 9:15, I think it's fine. Or 9:20, 9:20. And then I restart the meeting. So join again because I have some problems with the laptop. So see you at 9:20 and I will restart the meeting and then please join the meeting.
Okay.
Yes, it's work now. Okay, well done. Guys, Mona, Kamal, can you hear me? Yes?
Yes.
Okay. Because I can solve the problem without restarting. So the story of sediment transport or sediment load is a long story. So many years investigation, research. And if I want to summary it, it takes maybe 1 hour, 2 hours, but a very, very brief one. I want to tell you that a story. So sediment transport is divided to two things. Bed load and suspended load or wash load. So consider you have a river like this. So you have some sediment particles here. So this is bed load and some particles here. And this is suspended load. So bed load is near the bed and suspended load in the water column. So I think you know this. So sediment transport means we have two sections, section 1 and section 2. You have QS1 and QS2. Sediment transport from QS2 and QS1 is this value. So now you can distinguish between bed load and suspended load. And you know that for the suspended load, if tau 0 is more and more than tau c, we have suspended load. And for the bed load, if tau 0 is just more than tau c. So if the forces that I showed to you in the Kahoot, the active force are more than the resistant force, more and more. So we have the suspended load. Okay, let's go to bed load.
Sorry,
So yeah.
I didn't understand the shear, the difference in the shear for the suspended and separate load.
Yeah, so what is the incipiation motion? What is the condition which the sediment start moving? If you remember, the condition should be while the sheets as the stress of your flow is more than the critical stress. It's like the flow depth. If the y is more than yc, we decide about the regime of flow. It's like here, if the stress more than critical stress, or tau 0 is more than tau c, it's the incipation condition. For example, I just want to give you some numbers to understand it, but the numbers are not correct. For example, 5 is more than 3. So we have the difference between 5 and 3 is not too much. So we have bed load. But if you have, for example, 25 and 3, so the difference is so much, and it allows the sediment to coming in the water column to suspend the sediment coming up.
Now
You
I get
got it?
Yeah.
So I told you about the various bed loads equation. So we have various movement. For example, one is a sliding, one is rolling, and one is saltating. So based on that, we have different equation. Let me to bring this. Yes, you can see here, rolling, sliding, and saltating. Remember that. And I also want to, we can see a movie about it. You can see the movie, yes?
Yes.
Yeah. So it's a good movie to see the movement of sediments. Just look at the sediments. You can see sometimes rolling, sometimes sliding, and sometimes you can see suspended sediment. You can see sometimes the sediment jump and jump and jump. So now the man going to another part, which there is a rusted chain. It's something like a armor layer. And you can see because of this armor layer or this change, there isn't any scoring here or sediment movement. And also the material of sediment here is coarse, coarser than the previous one. So you cannot see any movement here. You see, can you see the rolling or sliding? Okay, so based on that, we have some investigation. For example, one, according to the assumption of movement, of sediment. For example, a sliding. I want just to tell you the story very briefly. So a researcher named Dubais is one of the pioneer of considering the sliding movement of sediments. For example, he consider this is your bed. He considers that the sediment movements are in a straight layer like this, a straight layer like this, and this is the bed load. And consider this d prime, the distance. And then computing, for example, using the weight equation, something like this, and then continue the computation of his specific formula. So based off this assumption, it has some integration and some calculation in the parameters that it's not necessary to mention, and I just saved the time. The other one, for example, use rolling. You can consider we have a sediment. So we have a drag force, uplift force, or the buoyancy force. And what is the other force? The weight. We can also add more weights. So he considered this and named this distance, for example, E1, and this distance E2, then compute the inertia, for example, F multiple of distance, and continue these assumptions to find an equation for the sediment transport. So this is inertia and this is force. The other one, for example, considered saltating or jumping. So Einstein is one of the researchers who considered these. For example, he assumed that you have a particle here and it's jump here. So generally, it is famous among the scientists that Einstein, the sun is a probabilistic person, and the father is a realistic person. So the son used the probability equations and continue these. And continue this method and find the bed load equations. Do you have any question? No? The other way of computing bed load is using the regression equation or experimental equation. Which you can find so many equations in the published papers, or for example, each day maybe we have specific equations. For example, I myself working on river confluence or the junctions of confluence, and I have 4 equations for bed load computing of that. And also we have some topics for master thesis about river confluence. Maybe Sujit also have your own equation for computing bed load. Yes? Not yet, but you have, I think, on for hydraulic part. Okay. So let's go to suspended sediment. I just forgot to mention one important things here. So we have too many equations, too many methods, and I will introduce some of them and show you which one is more famous. But a good assumption. Yeah, sure. Mm-hmm. No, it's not possible to do that because you have so many particles and you cannot detect each part. It's just an assumption for starting a developing an equation for that. For example, Einstein assumption, ancient method assumption is that it's most of them is sliding, and they developed a method and equation and then calibrate or validate their equation with some data. And I will tell you that we don't have any unified equation for bed load. There isn't any unified equation all around the world for bed load. We have so many methods and you have to compute them and see which one is better for your case, and then compare the results and find which one is better. I will also explain it. So you got your answer? It's an assumption. For example, you have so many of these assumptions in the hydraulic. Or yeah, for example, for the shields parameter, you have it in the previous lecture. The assumption is, I think the bed slope is not too much. So this is an assumption, and you will use the shear stress for example, while you have a slope. Or the sheets parameters, I think it's developed for the uniform bed material, but you will use it for the non-uniform. These are some assumptions that add some uncertainty in your results, and you have some error based on that. There isn't any accurate results because of these computations. You can compute or detect each particle, but it takes so much time, it takes so many expenses, and it's not possible or useful to do that. Okay. So good assumption. The bed layer. So as I said, we have so many equations, we have so many assumptions, but a usual and good assumptions that you sometimes you can consider it for computing the parameters. It's the bed layer is equal to 2. It is better to use this definition. 2 times of the diameter of the sediment particles. So I mean this, if I call this, so here, it's 2 ds. Approximately, it's an assumption. It's not the accurate one. But for example, if you want to roughly set that I have this bed layer height, you can multiply the sediment size by 2 and consider this as a bed layer. Okay, for the sediment load, yes, because the bed layer, the thickness is important for you. And if you have the height, then you have width and you can compute the volume of passing through that area. And also in suspended sediment, sometimes it's important to know the bed layer height. In the equations, you need that. So for the suspended sediment, I just go through it very fast because I will explain it. We have some integration methods. And we will use the advection diffusion equation or mass transport. I will explain it later. I just want to have this flow chart, or you can also, we have some experimental equation. Experimental equation means that you have a dimensionless parameters, and then you go to the laboratory or field and extract so many data, and then by analyzes them, you find an equation for the sediment load or sediment bed load, like the sheets or the one that I will show you. There are so many papers. For example, I think we upload one, Zanke. You can see that it's compare various methods, which some of them are using experimental equations. And for example, sometimes you can, if you don't have a good data, you can use some assumptions. Sometimes, for example, 50% of bed load in mountain area, sometimes 10% of bed load in flat or plain area. These are some assumptions which are different. For example, this assumption maybe it's not work for Germany or work for other parts of the world. Sometimes they evaluate some regions, some rivers, and they consider some assumption to make everything very fast. Yeah, I will explain it later. So do you have any questions? Okay, just go to the PowerPoint. I think we are here. So as I said, we have some methods for transport of sediment or transport formula. One of them based on empirical methods, for example, Shokolich, 1933. The other is related to bed shear stress approach. The other using energy approach, for example, by writing the energy equation in differential form, they extract or find an equation for computing the sediment load. And Young is also famous. He has also a book that it's really good book and you can study that. And some of them using regression approaches that I told you, by using the experimental data and using the dimensionless analyzers, they extract some equation. So these approaches were developed either for the determination of the bed load rate or the total load, So it is important to know that total load is the bed load plus suspended load. And some equations can estimate the total load, some equations can estimate bed load, and some of them can estimate suspended load. So you should be careful about using them. If they ask you what is the total load, you should use the equation which gives you the total load, or if you use the separate equation, just add bed load to suspended load. Yes, here we have some research that give us some methods for computing the bed loads. You know the shields, it's famous, but maybe especially in Europe, Peter is so useful and so famous. Van Ryn also is so famous, and they use a lot, we are using it in the softwares and codes a lot. Yeah, and for the total load, also Einstein, and also in the previous one, it's famous. Sometimes Engelon and Hansen is famous. And I will tell you when you should use which equation or which method. Yes, here. So there exist many different sediment transport formula indicating the complexity of the problem. And as I said, until today, there is no universal applicable approach for them. But as an example, we are going to explain briefly the Sheets method and Peter and Muller. So Sheets introduced this equation, which is easy to compute. You just know about the parameters. For example, you have Q here. It's the mean velocity. Multiplied by water depth, and QS is the GS. It's, if you remember, sediment transport. And if you insert these equations into the main one, then you have this. And you can also make it more simple, like this. It's not this. Yes. So if you remember, this is the sheets parameter. I introduced these parameters before. And you know that the sheets number is related to particle Reynolds number. So you have some example to solve, and just you need to use this equation and, for example, find the tau zero using gamma RS and put the data in it and then solve it. I think it's not a difficult one, but yeah, next session, you will ask Muli about this if you have any problem. For example, here you can see they use various data in this figure for computing this and this. And you can see in this figure, they have some errors here. And this is the way that they introduced this equation by Sheets in 1936. So the other one, Peter and Muller, based on their assumptions and calculation, they introduced this equation that you can see here. And it's important to know the parameters. So QB is the volumetric transport rate. So it's the volumetric. GS is the dimension of GS is kilogram per second. Here it's volumetric, like discharge. You can see it's the dimension. So be careful about volumetric transport rate or mass transport rate. Shields stress, that you know that. Critical shield stress, that usually we consider these. For example, Einstein has another value which is near to that, but this is the most important value for the critical shield stress. This is the tau C. This is the formula of that. So this is the new definition, reduction factor considering bed roughness, and Kr is the grain Stickler number, and you should compute it based on these Stickler equation, and dm is mean diameter, that you should compute it from this equation. It's the summation equation. So roughly speaking, or rule of thumb, if you want to consider the values of KST to KR, if the values are between 0.85 to 0.9, it's normal. If it's 0.75, large transport rate, and if it's 0.25, large bed forms. It's just estimate. It's not 100% accurate. Yeah. Yeah. This one. So you should make a, you remember that you have a graph of sediment. This is 100%, this is D. You remember that? So you have these value, accumulation probability of these. For example, here is 60%, this is P. For example, here you have D1 and this is P1. Yeah, if you remember the graphs. Yeah, exactly. If you remember the grain size distribution graphs, you can see this. I think you have it in the first lectures. You just need to remember, I think you have it in previous lectures, that you have how to distinguish between uniform sediment and non-uniform sediment. So that graphs, it's something like this. So this famous formula is developed at ETH Zurich, and experiments with uniform sediment and different densities. So this equation is, it should be good for uniform sediments. So if you have a case with uniform sediments, the result of this equation may be better, but you can also use it for non-uniform, but you should consider this fact, and when you want to compare the results of various equations, you should consider this. And the grain size that they use to extract this equation is between 0.04 to 30 millimeter, and the slope is this. So they assume these boundary conditions for developing this equation. So you have some limitation in this equation or some assumption. When you want to use for your case, you have to consider that. We have, for example, 100 equation. You should find which one is more appropriate for your case. For example, you see this equation, the slope is okay, and this equation, the grain size is okay. So you can use this. And then you use, for example, 4 different equations and then compare the results, because we don't have any uniform or any unity equations for computing bed loads. Yes, in this paper, Zanke and Roland, they compute various transport functions from 1948 to 2018. You can see there are, all of them are different with each other. You can see them. The results are different. Each one gives you different graph. Okay, here also you can compute G star based on Sheets number, and for various equations or various method, Meyer-Peter. And you can see each one as a different. For example, this is as this curve, this is as this curve. And if you want to use this curve, this is just a graphical method, and it's not always useful, but it's good to see it. For example, you find the Sheets number as this value, 0.04. It's like a Moody diagram that you use to compute F, the friction factor. And then, for example, use the Meyer-Peter and the curve coming here, and then you find this, for example. You remember the Moody diagram? You have a diagram like this. I think this is F, this is for various epsilon D, and this is for Reynolds. Then you have for various epsilon D. It's exactly like that, compute it. But it's good to see each method has different with another method. So remarks, as I tell you some of them, determination of sediment transport rate is one of the most challenging topics in hydraulic and environmental engineering. There exists many formula, but a general unifying formula is not yet available. More detailed theoretical work, considering different scales such as grain scale to reach scales, is on its way. Still, so many researchers compute or develop new equations for a particular case. And when determining sediment transport rates, only approaches should be used that were derived for the boundary conditions of the application case. I explain it now. You should use the equation or the method which has more similarity with your case. Any question? It is recommended to use not only one, but more approach to determine the expected range of transport rate. As I said, you should use, for example, 4 similar methods or equations, and then choose the best one based on your experience and your case. Sometimes it is possible to gain information from site investigation. For example, sometimes you sample a bed load and see the grain size, grain diameter, and monitoring the sedimentation in reservoirs, and they can help you to decide which one is better. Additional bed slope suspended load measurement are also helpful. Such information can be used to choose the most appropriate approach. And the other thing you should consider is sediment budget. We have some equations that we said, okay, this equation is good for computing sediment load, and this equation is good for computing the suspended load, but these are your expenses. For example, you want to buy a laptop, and these are the laptop price is, for example, 40,000 kron. So if you have that money, you can buy it. It's like here, if you have a source of sediment, then your values is fine. For example, if you have a landslide, if you have a fine material of sediment, I mean source of sediment. For example, you calculate the total bed is one value, for example, A. Then if you have this source of sediments, this source of erosion in your watershed, this value is correct. You got it? For example, you compute the sediment load of this value, for example. It's just an example, don't consider the value. But you have to have this sediment in your area. You have to have this erosion. For example, you compute for a river with coarse material, so this is not correct. If you have a sediment source that coming from upstream, so this is upstream, you compute sediment load here as this value. But the constraint is that you have this source of soil or sediment here. You want to buy a laptop here, but you have to have that money in your pocket to buy it. You got it now? So ask me a question if you need more explanation. So you need rest. Yes. I think we have it here. Yes, but I will show you here. I think we have it in the slides, maybe in the future slides. So here is the, oh, sorry, this is H. Submergence relevant. This is water head and this is the sediment size. If this is very high, I think more than 100, it's not effective. How to prove this? It's experimental. They do some experiments, so many values of H, ES, and epsilon, and they see after this value, it's not effective. And the reason is like it's for the pressure that you have. For example, if you have a high water depth, the pressure on the sediment size is more than the low water depth. So it's effect on this, but how you compute it or what is the limitation? Is it correct or not? They found it on the laboratory or based on experiments. And is it open? Yeah, please. Again. Okay. Generally, sometimes it's not correct always. For example, you are talking about this assumption that I said, yes. This is an assumption. For example, when you don't have enough information or enough data to compute the bed load, you can use this assumption. but this is not 100% accurate. As I said, you can use monitoring the bed material or sample some bed material to see it. But if you remember the video that I show you, you can see that, or you can search it in the internet. You can see it's almost correct. You can see, for example, 2 particles of sediments. It's going at the bottom of the flume or at the bottom of the river. So you can almost see it, but it's just an assumption. And also the percentage that I told you, it's just the assumption because it's really hard to find the accurate value of this for the cases or for the projects or for rivers. So it's just an assumption, and you should, if you want more accurate result, you should investigate more on that specific case. Yeah, you got it? Good. So yes, till 10:15. I think you need rest.
Can I ask a question?
Yes, sure.
When the velocity of the water is lower and we have lower discharge, silt materials will settle down and they become like a bedrock.
Could you please repeat it? I can't hear it very well.
When there is a silt material in water, when the discharge and the velocity is lower, they will settle down and they will not be suspended anymore. Can we call it
I
bedrock?
cannot hear it very well. Can you write it in the chat? Maybe there is a problem with my. Yes, it's good to write it in the chat again. No, lecture till 11, and then you have, I think, exercise with Muli to 12 or 1, I think. Yes. Yeah, but our class is till 11. You are writing it, Mona?
Yes.
Thank you. I see it. Silt materials, when they are settled down while the velocity and discharge is lower, can we call it bed load? No, 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 no. It's completely, I think, different names. So let me show you here again. You have a river like this, and then you have a reservoir. And this is your water surface, and this is your water surface of this reservoir. So here the velocity is almost 0. It's the case that you said.
Yeah.
And this is the V that you have here. And you have some bed load here and some. So this is suspended load. And this is bed load. And the sum of these two are sediment load. So they are coming to the reservoir, and this is here you have a deposition. For example, you have here the deposition. So we call it deposition.
Okay.
Or aggradation of sediment. This is the phrase that you should use. So what is this value, or what is the quantity of these? This is coming from bed load and suspended load.
Okay.
You got it?
Yes.
The name is aggradation or deposition or sedimentation. But the quantity of that is the summation of bed load and suspended load.
Okay.
I mean, your sentence is correct, but you should rephrase the names and words.
Okay.
Yeah, good to ask it. Okay, see you at 10:15.
And sorry, your PC is, I think, out of charge.
Yeah, I have to bring it a charger. Okay, I should go up. Okay. So if you don't have further questions, let's go to the suspended sediment. So here you can see the suspended sediment. Suspended sediment is change the water color. You can make difference from these. We have some famous rivers that half part is dark like his and half part is not. One of them in Zurich and the other one is, we have some, which I think you see the photos. So suspended sediment transport occurs when turbulent velocity fluctuation are large enough to maintain the particles in the water body without frequent bed contact. The one that I told you, tau should be more and more than critical one, or v, the velocity should be more and more the critical velocity. It's coming from this. The amount of transported suspended sediment in lowland rivers represents approximately 85 to 95% of the total bed. This value because of you have lowland rivers. Lowland rivers usually has a poor soil or it has a very fine sediment size. For example, the average suspended sediment load in German rivers varies in general between 20 to 100 gram per volume, resulting in relatively large annual transport rate. Suspended load transport rate can vary quite significantly as they are directly linked with turbulence, discharge regime, land use, and etc. So it's so dependent to your watershed conditions. If you have a watershed with poor soil structure, so you have more suspended sediment. So here you can see a table for average annual load or soil erosion for various time series. You can see the average load or soil erosion for different rivers. These are the stations and this is the kilometer of that station. And you can see the catchment size here. It's so much. It's the magnitude is completely different, or you can compare it with this. The catchment size of third one, this one is around 4 times less than the first one. And you can see the discharge here is higher than discharge here. But the average load here is almost the same. So the reason is the soil structure or land use. Maybe they, in that field, they construct a dam or construct something that they have a lot of landslide. I mean, they have more sediment budget or they have more sediment source. And this is the value on tones, and this is the soil erosion that they compute per area. And here you can see time series at a specific year, 2004, for various famous rivers. You can see the soil erosion and average annual load, and you can compare them. So here at the same time, you have different discharge and different load and different soil erosion. So it is related to events. For example, in that specific year, you have a large flood or heavy floods that makes more sediments or makes more erosions in compared to another year. So there are some example of maximum transport load. You can see 15.5 here for Astria River. This river is a Tiber River in Italy. It's I worked there. It's really amazing river and large. And this is a famous river in China. You can see the values. Yes, here there is a sort of largest river in terms of suspended sediment load. At the top, you can see Amazon with this value in ton, average annual suspended load. After that, it's this river. This river is so famous, and I think it's famous also as a yellow river because of the large amount of the suspended sediment. The color of the water of this river is almost yellow because of the suspended sediments. So it's famous as a yellow river. Yes, this is the one that I told you. The geology condition of your watershed is an important, and you have to consider that. And also which type of sediment you have. Is it high density, low density? What is the sediment size? All of them are important. So suspended sediments are much more influenced by the cycle between erosion and sedimentation than bed load. For example, in zones with low turbulence, like side arms, exposed harbors, and etc., suspended sediment can be deposited, resulting in bed aggradation and loss of retention area. So some areas that the turbulency in the flow is less or the velocity is less, there is a chance for sediment and suspended sediment to deposit or aggradation or sedimentation. These areas, for example, side arms or exposed or harbors, I think maybe you don't know exposed. It's some meandering rivers or some rivers going like these. It's like exposed, and after some years, when the river develops, it's going to be, for example, straight, and then it's diminished after some years. For example, I think here you can see this. So after so many years, it will be like this. You can see here, this area separate from this. Okay. The next remarks that we can get from here, it's the deposition of suspended sediment. It's also often a problem. as pollutants are often directly coupled with suspended sediments. For example, you have a pollutant in the water, and the problem for us to compute the sediment, the suspended sediment, is that pollutants change the, for example, density of water or change other parameters. So as a case study, we have this famous lake in Bavaria in Germany, Chiemsee, which has a significant deposition of sediments. Between 1926 and 2000, the annual volumetric transport rates of suspended sediment varied between 1,000 to 450,000 cubic meter. However, within single events up to 185,000 cubic meter of sediment can be transported within the lake. So the annual rate, the average annual rate is this, but maybe in one event you have it more than the average one. You can see it here. You can see so many deposition in this area, and you will be surprised with next slide. So many years ago, the area of the lake is 300 cubic kilometer, but as of today, today means some years ago, it's 80 cubic kilometer. So you can see the differences here. And the depth decreased from 250 to 73 meters. So they should use some methods to conserve the watershed. For example, build or construct some small dams to catch the sediments at the upstream and don't let it come into the lake. But the other benefit of this, they can, because the sedimentation in the lake, the soil is so strong and useful for agricultural purposes, so they can extract it and use it. And of course, they sell it to the farmers. And the values of bed load you can see here, and the suspended load you can see. These are the high value of this lake. And one of the reasons that you have this value is the fine coarse material of the bed load and also high slope of this area. So this is an example. You can see, I think these area just added after the sedimentation, and it's very good for farming. You can see they have some farms here, and these are new developed area here. Yes, the investigation showed that approximately 80% of the suspended sediment originate from an upstream area, which is geological mainly composed of gray whack, a sort of unstable sandstone. It's a specific sandstone. You can see it here. It's really unstable, and after collide to each other, they destroy and to so many fine parts. The comparison of recent surveys with older ones shows that the delta advances in the last 200 years by with 3.2 cubic kilometer. Okay, how to estimate suspended sediment transport? We have some equations, but how they start to develop these equations, I explained a little to you in the previous lecture. If you remember that. I also can explain again. So generally the mass transport divided in two parts by advection and diffusion. So advection is like the effect of force. So based on the force, it makes the sediment movement. Gravity is the main force. And you know the diffusion. The diffusion is changing in concentration. For example, if you drop a color into a water, you can see the color moves because of the changing or different concentration between the color drop and the water column. We have also some other phrases like dispersion. Dispersion is more related to while the sediment particles collide to each other by accidents. So when they collide to each other, you have these particles, they are collide to each other. So some of them goes up and some of them goes down. This is they call it equilibrium condition. So for example, you have so many cars in this way, they collide to each other. So some of them goes up and some of them goes down. A general way of computing the suspended sediment, imagine that this is bed load. This is D, and you choose element as Y. It has its own concentration and V. And you know the V is coming from logarithmic velocity equations that you have, for example, something like this that we talked about it in the previous session. So what is the suspended sediment discharge for this element? You have a velocity, you have a concentration, and then you have this is the area is this. So it's C multiple V multiple A. Remember the simple equation of discharge? It's velocity multiplied by V. But you have a concentration, not 100% of this element goes. For example, the concentration is 60%. So you have to consider that. This is the reason that we use concentration, because the sediment included in this element, for example, it's just 70%, 60%. So this is the mass transfer or suspended sediment for this element. So if you want to compute it for the whole, this water column, you just need to get a integration from, so this is A, from A to D. So you can write an equation for suspended sediment for this element, then you get integration from A, this elevation, to this elevation. It's a simple way to compute it, but I will go through the slides which are more important. And just remember, sometimes the maximum of C is 60 point. This is another assumption for calculating the suspended sediment. Usually it's the maximum one is like this. For example, in the examples that you have, directly they ask you to consider what and to compute from which equations. If you see they use this is the maximum and usual number. In water column, usually. It depends to the case, but if you don't have any information, you don't have any data, then you can assume this value. Okay, we are here. So this is a general equation of suspended sediment transportation or advection diffusion equation. The source is this. You can go through this paper to know more details about it or read the papers. But I try to introduce some parts here. Yes, if, for example, you see your questions or your problem tell you consider the maximum one, you can assume this, or if they give it to you, you can assume this. Otherwise, in real cases, if you don't have any data, you just want roughly compute the suspended sediment, you can use this value. They will tell you to consider that or not. Okay, the calculation of suspended sediment transport rate is based on the advection diffusion equation describing transport phenomena due to advection and diffusion that I told you. Advection is a transport mechanism of a substance or conserved property with a fluid motion. You can see there is a sediment, and this is the usual form of equation. Rate of mass transport per unit area equals to product of sediment concentration, this, and the velocity component. And diffusion, molecular diffusion describes the scattering of sediment particles by random molecular motion as described by Fick's law. If you search the Fick's law also in the internet, you can see it has 3 different rules. For example, one reason of motion is that the particles or moleculars collide to each other. So they add some forces to each other. It's like internal forces. So it's some law which is not so important here. Yes, and this is the equation for a slow movement. Imagine that you have a glass and you add some very fine sand on this glass, in this glass. Then you put your spoon and slowly turn your spoon. This is somehow, this is a concentration. Here we have a example of coffee. It's almost like a silt. This is a concentration profile, and this is the equation, and D is the diffusion coefficient. You have it here. C is concentration, and rate of transport is proportional to concentration gradient. The minus sign indicates that the mass flux is directly toward the direction of decreasing concentration. And here we try to show you the effect of turbulent mixing. When you turning your spoon very fast, you make something like a vortex in the glass full of sand or coffee. So it has another effect which called turbulent mixing. And you can see the concentration profile is not, it's more complex. You can see it here. And we have another coefficient for that, which is turbulent mixing coefficient. Epsilon C is, as always, concentration, and mass transport is proportional to the concentration gradient. It means this one. So motion of sediment particles due to turbulent fluid motion, you can see it there, more effective than molecular diffusion. The molecular diffusion coefficient is several order of magnitude smaller than the turbulent mixing coefficient. So if you have turbulent mixing coefficient, it's really effective. If you have, I explain a little about dispersion. You can see we have advection here, that the particle goes straight, but simultaneously we have the mixing, and this is the effect of dispersion. And the value computed as this is the advection, and this is the dispersion coefficient. A process acting in flow direction combining the interaction between advection and turbulent mixing, this dispersion coefficient is usually very large. So this is our advection diffusion equation, but we consider an assumption. We have a steady uniform turbulent flow. So it means each parameter to T, you consider it at 0. And wide rectangular channel, so you have just Z, has no sediment source and sinks. This is a assumption or limitation that we add to our equation to make it more simple. So in this way, we ignore these terms, and then we have this final equation. This means we only have to consider the vertical direction and can neglect the molecular diffusion coefficient of T. So as you know, the left hand side here represent the advective term, and the right hand side is turbulent. So this is turbulent, this is advection. The advective term results from the settling of particles due to the density difference between the particles and the fluid. So then if you integrate from both sides, you have this equation. So you remember that I talked about equilibrium condition. I told you that they collide to each other, and some of them go up and some of them go down. So it's a equilibrium condition. The summation or the total of this is you have some constant sediment as a suspended load on the water column. So the turbulent mixing is in equilibrium with advective transport process. So another researcher, von Karman, add another assumptions to these computations. For example, he considered epsilon z as a beta multiplied by epsilon m, and he introduced this value means kappa. This is like K. This is a von Karman coefficient. It's just a story behind the final equation. I am telling this story very briefly. So beta is usually 1, like the beta of the velocity, is the ratio of the turbulent mixing coefficient of sediment to the momentum exchange coefficient, and usually we consider it as 1. And you know U star, but the new one is kappa, is the von Karman constant. So the derivation is based on the general case where the turbulent mixing coefficient varies with depth. You can see values of epsilon z according to the various depth. And so von Karman considered this equation, and if you insert this assumption to the equation that we had, it's coming from this one, coming from the advection equation. Results, we have this final equation, which usually you use to compute the concentration at different locations. So you know Z is Ross number, you should consider this. This is important. And Z is a vertical coordinate, this Z, and H is the water depth. You know the Ross or Ross number. Sometimes it's the symbol change in different references. Sometimes they show it as a R0. Ca is the reference sediment concentration at a reference elevation above the bed. And A is often determined at AH to this value. We have yes. So for example, you have, this is the concentration profile. This is H. And you want to compute here. And you want to compute, for example, CA or C. Usually you have CA and you want to compute C as this location. This is the point A. So CA is the reference sediment concentration above the A. You have one example of this that Muli solved this, and you can see so many examples of this in the books and papers. So I think you have this diagram for Ross number. You know that as the Ross number decreases, a great fraction of sediments will be transported in suspension. So suspension becomes significant for these constraints. If you have these conditions, the suspension is significant. And for Z more than 2.5, most of the sediment will be transported close to the bed. So this is for bed layer. And you can use this graph for various U star over the velocity. you have values C over CA, and this is the other parameters. So imagine your U star is 40, and you have these comes here, and this is the value that you have here. You can see so many methods like these, graphical methods, equations that you can use to estimate the concentration at a specific point or a specific height. Yes, you have it in lecture 1-2, these values. So Rose number, as we said, it's a method for estimating the movement of sediment. It is bed load, it is suspended load, or it's in the transition zone. Yes, this is the dimensionless grain diameter, and this is the toe star. For example, you compute that your points coming here, and you know that you have dunes or ripples, and it is bed load or it is suspended. These are the general methods for computing the various shape of the sediment movement. And you know what is dunes and ripples? We have some bed form like these. You can see near the beaches, for example, some bed forms like these. Did you see that? This one. So it's named as ripples or dunes. When the height is more than 10 centimeter, it should be dunes. So the big one is dunes, and the smaller one called ripple. And they have so many details, and if you want to go through it, they are dependent to the regime, the flow regime. Is it subcritical, critical, and so many details that you should go through it. But it's important to at least know what is ripple and dunes, because it's changed the. So here, for example, this is the ripples, for example. And this is a river without ripples. This is change your roughness coefficient, because the roughness coefficient is considered of two things. One is the DS, or grain of sediment. Is it glass or is it a concrete? It depends to the resistance that you feel. And the other one is the shape form. You can consider this shape form as a roughness coefficient. So I think it's obvious that in this case, we increase the roughness of the bottom of the river because we have more resistance on the flow. No question? Oh, the time is over. So these are some parameters that you can read it. It's a mass concentration. C is the mass of sediment particles to the volume of water sediment mixture, and volume concentration. You can see it's volume, and here is the mass. It's just some definition that you can read it. Yes, the other definition is the weight concentration. We use weight. You don't have any written exam, but in the project, in your project, be careful that they ask you find the bed load in mass or in volume. And the concentration in parts per million ppm, you have these, and this is another definition that you can find in this paper. Knowing the concentration profile, the unit suspended sediment discharge can be computed from the depth integrated advective flux of sediment. So you remember this? No? Yeah, this is the one that I tell you here. Where is it? This one? No. I think this one. This is this equation. It's the same. So I pass it. I explain it here. And the corresponding total sediment load is obtained from integration of the unit suspended sediment discharge over the entire width of the channel. So this slide exactly the explanation that I gave to you in the blackboard. So do you have any question? So it's a large story with so many equations that you don't need to memorize them. You just need to general things like mining is useful in turbulent flow justice, and when you want to use it in the projects, you can open your book or you can open the equation, and sometimes they, for example, in the example, we give you the equation, and then you can easily just compute the parameters and add it to the final equation. So the last PowerPoint, which is more details for you if you want to study, it's talking about the settling velocity that I think you have it in previous lectures or maybe in future lectures, but it should be before that our lecture. And you know that we have a sediment and we have a forces. If the effective force more than resistant force, it's going up, and if both are the same, it's stay in the column of water. And the parameters which affect that is here. And then you have, you know, this is the effective forces and resistant forces. And the important things here is CAD, just for your further information. CAD, it depends to the shape of the sediment particle. For example, if you have this particle and this particle, the settling velocity is different. Imagine that you want to drop two balls with a same weight, but with different shape. So the resistance is different to coming down. And you can read other things for your further information if you want. Yes, this is the things that I told you. The forces are equal. I can't see anything special here. Yes, this is more information about these equations. If you need more details, you can read it later. And also you can see so many books, Young and other books, to have more information about it. So if you have any questions, you can send me email or ask it now. And yes, Muller is waiting for you to solve more example. Okay, thank you. Do you have any questions, Kamal? Because I want to turn off the recording. Okay, thank you. Yeah. And have a nice time in your next session.
Thank you.
Yeah, you're welcome.